Hello all, I want to welcome you once again to today's lecture. Today we'll be finishing with the last topic of our module 6, and today we'll be talking about phase changes and the heating curve. But before we move on, I have a beautiful quote for you. The quote says, "Life is tough, but you must be tougher." Of course, most times when we go through life, we encounter some challenges. Now, those who persevere to the end will always overcome these challenges. And this is just my message before we get into the class. All right. Now, in this lecture today, there are two things we intend to achieve at the end of the lecture. Number one, we're going to know how to draw the heating curve, the heating and the cooling curve. And then as we draw that, we're going to label it well. You label, you're going to indicate different phases or different states of matter in the heating curve. And number two, we understand how to do calculations based on changes, energy changes that accompany cooling or heating or change of state of matter. Of course, when matter changes state from when matter changes its state from one state to another, when you change it from gas or let's say from solid to liquid, from liquid to gas, and vice versa, we know that energy is either added or removed. And how do we calculate or take into account of those energy changes that are involved? And those are part of what we're going to be achieving in the last part of this class. Let's take it off from there immediately. The specific heat capacity. The specific heat capacity measures the amount of heat needed to raise the temperature of a substance by 1 degree Celsius. Is a kind of measure of the ability of substances to hold, I will put it that way, to retain heat themselves. So if particularly interesting, most non-metals have high specific heat capacity S. High S. Let me just say S alone. High S. Whereas metals have low S. Why? Let's try to explain this. You see, metals easily gain heat and lose it immediately. They easily gain it and lose it because they are good conductors of heat and electricity. However, the non-metals do not gain heat immediately. So it takes them time to gain this heat, but when they gain this heat, they retain it as long as possible. So that ability of a substance to retain that heat is actually what the specific capacity actually measures. So that amount of heat you're going to need to raise the temperature of that object by 1 degree Celsius. 1 gram of a substance by 1 degree Celsius. And it is actually measured in calories per gram per degree Celsius. Now, there are other units of measurement like joule per gram per Celsius or kilojoule per gram. But in the course of this class, we're going to be skipping to this particular measurement in calories per gram per degree Celsius. Now, so the heat either released or gained when matter changes heat can be expressed in this formula, can be expressed as this, where Q is the heat in calories, the mass will be in grams. Now the specific capacity, like I said, has to be in calories gram per degree Celsius so that our unit of grams and calories will cancel. And then this, remember, this is the mass, this is the specific heat, and delta T simply means change in temperature. And change in temperature means you're going to have the initial temperature and the final temperature before you heated and after you'd have heated. And when you subtract that difference in temperature, if you put that in this formula, it's going to give you the quantity of heat that is that lost or gained at that specific change of matter or a change in temperature. Let us take it further from there. Heat of fusion and heat of vaporization. You see, heat of fusion is defined as the amount of heat required to melt exactly 1 gram of a solid substance at a constant temperature. You see, if you're going to melt a solid to liquid, remember, melting simply means you're going from the solid state to the liquid state. Now, something is happening here. What is happening here? There is what? A change of state. Let me put it there. There is a change of state. Let me try to put it so clear. So there is a change of state happening here. Now, anytime a change of state is happening, well, let me try to make that thing clearer. Now, anytime a change of state is happening, the intermolecular forces or the intermolecular bonds holding the molecule together is being broken down. Remember, change of state is a physical process. We're not talking about chemical bonds. We're talking about those intermolecular forces we talked about earlier, like the hydrogen bonding, the dipole-dipole, and the dispersion forces that is holding the molecule together is being broken down completely. And that is exactly what is happening here. So the amount of heat needed for that process to take place is what we call what? Is what we call the heat of fission. On the other hand, the heat of evaporation is the amount of heat needed to vaporize exactly 1 gram of a liquid substance and then change it to what? To gas. So here we're going from liquid to gas. That's what we call, of course, that is what we mean by vaporization. And that quantity of heat you need. Now, in vaporization, something interesting happens. You see, in fission, you are just breaking the intermolecular force, disrupting the solid structure to become liquid. The bonds are still intact, not completely broken. In vaporization, those bonds holding those liquids together are completely shattered, that the gas molecules will now escape and don't take account of each other. So in this case, there is total breakdown. There is complete breakdown of intermolecular forces, complete breakdown of IMF in this case. And in fact, that is the reason why the energy needed to carry out, the energy needed to vaporize a liquid to a gas is far greater than the energy used to melt a solid to liquid. And in fact, let's take an example of water. Now, the heat of fission of water to change an ice, 1 gram of ice, to liquid water, you just need 80 calories per gram. However, if you're going to vaporize 1 gram of water to steam, you're going to need 550 calories. And that explains the reason why steam at 100 degrees Celsius is going to have more severe burn than water that is boiling at 100 degrees Celsius. And part of the reason why we do that because is that we know that the gaseous state is the most energetic state of matter. And at that point, remember what happens? Molecules are moving so fast. And remember, when molecules are moving so fast, that is a measure of the average kinetic energy of those molecules. We take it off from there. Energy and the change of state. What is now happening? You see, pure substances in gaseous state, I already said that, contain more energy than in the liquid, and I would have added this, and solid state. They contain far more energy than the solid and the liquid state. Of course, increase in temperature. Anytime temperature, remember when we talked about the kinetic theory of matter, or even that of gas, we said an increase in kinetic energy corresponds to increase in temperature. So increase in temperature always corresponds to increase in kinetic energy. And what that means is that the velocity of the molecules, or speed, will increase. You're increasing the velocity of molecules. Increases. However, at change of state, something different happened. At change of state, what is happening here? Let's look at change of state. Now, adding heat does not correspond to increase in kinetic energy. And if this increase in kinetic energy means increase in temperature, it does not correspond to that. Look at this word, it's important. It does not. So as I was saying, now, the energy you added at this point, at change of state, the energy being added only corresponds to increase in potential energy. Now, the energy here only corresponds to increase in potential energy and not in kinetic energy of the particles. What that simply means is that if it does not correspond, remember, temperature is proportional to kinetic energy. If that energy does not correspond to increase in kinetic energy, there won't be any temperature change. But since it corresponds to potential energy, remember we said that potential energy is the energy as a result of attraction or repulsion. Actually, what is happening here is that the energy used at the change of state is only needed to do what? To change the state. And what it does is that it breaks the intermolecular forces and make sure, and if it is from solid to liquid, it disrupts it and makes the change of state to occur. If it is in liquid to gas, it breaks the intermolecular forces to the dipole-dipole, or in the case of water, the hydrogen bonding, and makes all the molecules of water to become gas or steam. So at change of state, in those two places of change of state, when they're going from solid to liquid or from liquid to gas, what is happening is that the energy added is used to carry out a change of state, which only corresponds to what? Increase in potential energy. Now, this is better understood in this curve. This is what we call the heating curve, the phase changes and the heating curve. Now, in this curve, the curve is usually a plot of temperature at the y-axis versus heat at the horizontal axis. Yeah, the vertical versus the horizontal. Now, this shows you all the three states of matter. I tried to make this thing, and I do hope that you guys can see it very clearly. I have made this image myself, and it actually took me time to do that in the software. Now, let's look at what is happening now. So we're going to start with ice. We start with ice. Oh, something is high. Oh, something is not very clear. Now, what I have here is my Q1. Sorry for that. I didn't see that this moved. At times, this thing they tend to move, you know, but this is Q1 here. Now, this is my Q1 here. Then others actually clear enough and they never moved. Now, what is happening? So if I start with an ice and I start adding heat simply means heating. I'm heating it up. That is why this is the heating curve. I'm just heating it. And then my temperature is on the vertical axis. I start with the ice at negative 20 degrees Celsius. I start heating it up. Now, the first thing you do, immediately I start heating this ice, there will be a sharp increase in temperature from negative 20 degrees to 0 degrees Celsius, which is my first point of contact, which is A to B. At this A to B, the amount of heat needed can be calculated by calculating the slope. The slope at this point, at this heat, is Q1. If I calculate the heat added at this point, that gives me the amount of heat I need at this point. And then, after that point, what is happening now? What is happening here is that there is change in temperature. Anytime there is change in temperature, it corresponds to, remember, anytime there is increase in temperature, it corresponds to increase in kinetic energy of the molecule. So that is exactly what is happening here. Now, at A to B, at B to C, what is happening? Now, at this point of B, remember, here we only have solid. At B, you start having your liquid and your solid. We'll start having some water and some ice as a mixture at this point. That is what is happening. So from B to C, you have a mixture of water and ice. So this is your ice, remember? And now this is water at this point. So from B to C, what is happening here is that there is a change of state at this point. So every plateau, this plateau represents the change of state from solid to liquid. That is exactly what is happening here. Now at point C, all the solid that would have melted to liquid. So at this point, we only have liquid. At C, we only have liquid. At point C, we only have liquid at this point. That's what we have at point C. And then from here again, if you keep heating, remember you're adding your heat constantly in calories. If you keep heating again, you notice another sharp rise in slope. But this time, the slope is sharper and actually longer. Takes a little bit of time. Now, what is happening here is that from this C, where you have only liquid water, all these places you have your liquid water. You kept heating it from C to D. At the point of D, what is happening again? At the point of D, you start seeing steam or your gaseous water. So the whole of this point is liquid. This is what liquid. The whole of this slope is liquid. Remember, the whole of this slope here is just solid. Now this is a mixture. This here mix a mixture of solid and liquid. Here again will now be a mixture of what? Liquid and gas. That's what you have here. So this place means liquid plus gas. That's exactly what you are seeing here. Water being boiled and is boiling. They have the liquid and gas bubbles are coming out. So from D to E again, what is happening? If you look at this, this is a long plateau. Remember, every plateau, like I said, represents what? A change of state. Because what is happening here is that the water molecules are being heated so that the hydrogen bonds are being ripped off, and at this point they're going to become gas. So at this point at E completely, you're going to only having gaseous water, or what we call the steam. That's what you'll be having at that point. Here now you're going to be having only gas itself. And at this point, all the water molecules should have been converted to steam. And again, you have only steam here. When you begin to heat this steam again, you're going to be heating this steam from E to this. It's going to go from 100 degrees Celsius to 1. Remember, water boils at what? Water boils at 100 degrees Celsius. And then water melts, solid water or ice melt at 0 degrees Celsius, which corresponds to what we have here. So this curve is actually what we call the heating curve, when you are adding heat. And this process is an endothermic process. Now, the opposite of this process is the cooling curve. The cooling curve is an exothermic process, which is going to be the direct opposite of this. And in fact, the calculations of the cooling process will always be exothermic and will be a negative sign, because you are removing heat in that process, as we're going to see as we move on in this class. Now, let's now put those things we just said about this curve into, we're going to put it much more or less into perspective mathematically. So at that phase change, remember I said 1 gram of ice at this temperature was heated until 120 degrees Celsius of heat. If you go back to that, that's what we have, from -20 to 120 degrees Celsius, and we have just 1 gram of ice. Now, if you want to calculate the total heat needed in the whole of this process, remember this involves a 5 process. From A to B, remember what I said, involves ice. What is happening here is that you are heating the ice to a melting point. Ice was heated from, remember, it was heated from 0 degrees, no, from, not 0, from -20 degrees Celsius to 0 degrees Celsius. That's exactly what happened here. A to B. And the heat needed here is Q1. And Q1 can be calculated by taking the mass of this sample, which is 1 gram, times the specific capacity of ice, which you're going to get here. This is the specific capacity of ice, times change in temperature. Now, that is what is happening here. Anytime there is a change in temperature, you must have to do a change in temperature formula as T2 minus T1. Or you can just say change in T. That's exactly what it is. Now, from B to C, remember again, from B to C is the change of state. In change of state, there is the melting of an ice. We are going from solid to liquid. The formula you're going to use is Q2 is mass times heat of fusion. Heat of fusion, remember earlier I told you, is the amount of heat needed to melt exactly 1 gram of any solid heat it until it becomes a liquid. The heat needed for that process to occur is what we call the heat of fusion. So the heat of fusion is a constant. What do? You're going to get the heat of fusion. Oh, I think I made a mistake earlier, sorry. For the first one, you're going to be using specific heat capacity of ice. And for the second one, you're going to be using, that was my mistake, sorry. For the second one, from A to B, you're going to be using specific heat capacity S of ice. That's what you're going to be using here, S of ice. Now, for this one, you're going to be using the heat of fusion, and it's written there anyway. Don't mind my mistake, sorry for that. The heat of fusion of ice is going to be 80 calories per gram. So you're going to take this mass, you multiply by the heat of fusion to get this. Now, going from C to D again, let's see. If you're going from C to D again, you are just hitting what? If you look at this, this is a slope. And every slope tells you what? There is what? A temperature change. Remember, this means there's a temperature change here. Every slope tells you a temperature change. That's what you have here. This is a temperature change. So, again, there's a temperature change. And when there's a temperature change, that means you're heating it from what? Remember, from here now, there's no temperature change here. No change. Okay. Let me put it this way. No change in T. Again, for this one, there is change in T. And the change in T here is going from what? They're going from what? Again, let's look at it. I know what it is, but I want to show you. You're going from 0 to 100 degrees Celsius. So you're going from, again, 0 to 100 degrees Celsius. That's exactly what is happening here. Now, and what are you going to use? You're going to use the specific capacity of liquid water, because what you have there is water at that state. So this is what you're going to use, liquid water, which is 1.00 calories per gram per Kelvin. And after that, again, what do you now have the longest plateau. The longest plateau here is showing you that there is a change of state from liquid to what? To gas. That's what is happening here. And that's exactly what we're seeing here. And again, anytime there's a change of state, it does not involve no change in temperature. And you're going to be using the mass times the heat of vaporization. And the heat of vaporization of water is 540 calories per gram. The last but not the least, you know, at that point, at point E, you just have only what? Only gases. So at point E, you have only gas. And now you're heating your gas from 100 degrees Celsius to 120 degrees Celsius. Again, at this place, there is no change of state. Rather, there is change in temperature. So there is change in temperature. And change in temperature simply means you're going from 100 degrees Celsius to 120 degrees Celsius. And when you do all this, calculate all these things and add all of them together, that gives you the total amount of heat needed to change 1 gram of ice to steam at 120 degrees Celsius. And let us see how this is actually done. So let's try to put those things in practice. Let's just try to do all of them. So Q1, of course, is going to give me, of course, I wrote the formulas are here already. I'm not going to repeat them. Just follow along as I do it. So it's going to be 1 gram. We started with 1 gram for all of them, and you multiply that times the specific capacity I showed you already of ice is 0.48 calories, and then you're going to have per gram per degree Celsius times. Now there is change in temperature here. The change we have here is 0 degrees minus 20. And when you do this bracket, of course, everything at 0 degrees Celsius is going to give you, if you cancel out and see, so this, we cancel this, this, we cancel this, and your answer is actually going to give you 9.6 calories. That's what you get in the first one. For Q2, well, let's do it. For second one, Q2, for Q2 again, the formula we have there is, remember, is mass times heat of fusion. The heat of fusion of ice, again, is 80 calories per gram. So we're going to multiply this times the heat of fusion in the previous page, and it is 80 calories per gram. Remember, this is a constant. If you cancel these two, it's going to give you, of course, if you cancel this and this is going to give you 80.0 calories. That is the heat needed. Again, we go back. Q3, what do Q3 give us? In Q3, again, Q3, you're just talking about the change in temperature now. You're going from heating the water from liquid till it begins to, not it becomes, it begins to form gaseous water, which is steam. And there is a change in temperature. So that is going to be mass times the specific capacity of liquid water times the change in temperature. And that will give us, of course, the mass we started is always this, times the specific capacity of water, the liquid water, like I showed you earlier from that place, is just 1 calories per gram. So 1.00 calories per gram per degree Celsius times change in temperature. You went from 0 to 100. So the T2 is going to be 100 minus 0. Of course, this is in degrees Celsius. And again, when you cancel out this, and cancel this and this, your answer, if you multiply everything together, it's going to give us 100 calories again. Now we go to the next one. In Q4, which is the longest one, which is the place that the most energy was given off, remember, because it involves a change of state that involves breaking of what? The hydrogen bonds. Now we're going to be using the heat of vaporization, which is 540. Remember, this is what is happening here. So the heat of vaporization, that's what we're using. So we're going to go there. We're going to say the formula is going to be mass and the heat of vaporization. Again, we have it as 1.00 grams. We're going to multiply that by the heat of vaporization is 540 calories per gram. Again, when you cancel gram to versus gram, you multiply everything together here, you're going to get 540 calories. Now, the last but not the least is going to be the Q5. The Q5, you are heating steam at 100 degrees Celsius to 120 degrees Celsius. Again, there's a change of what? Temperature. So mass times specific heat times a change in temperature. So we have usually our mass is 1 gram. We're going to multiply it by, if you look at the heat capacity of ice, it's the same thing with of steam. It's something with that of ice. If you look at 0.48, so we're going to put it there. So it's going to be 0.48 calories per gram per degree Celsius. You're going to multiply that by 120 minus 100 degrees Celsius. Try to put my degree Celsius outside. Degree Celsius. And again, if you cancel out everything, you see this will cancel this, this will cancel this. And if you multiply everything together, we're still going to have 9.6 calories. Now, so I'm going to write this one with the color I use for others too, so that it doesn't confuse you. So this is still going to be 9.6 calories. So the total amount of heat needed to convert this thing will be the summation of all this heat. So our total amount of heat is going to be, if I go back to my red, Q total is going to be, adding everything here together. So if you add everything, it's going to be 9.6 plus 80.0 plus 100 plus 540 plus 9.6, and this will give you 739.2 calories. So this is the amount, this heat, this quantity of heat represents the total amount of heat needed to convert 1 gram of solid water or ice from -20 degrees Celsius to 120 degrees Celsius. And this is done by addition of heat. And in fact, it is an endothermic process. So remember, heat was added. This is an endothermic process. Endothermic process. Heat was added. Heat was added. And again, remember, now when we are doing the cooling curve, assuming we're going to use all these values, the cooling curve will be exactly the same amount of this heat, but the negative sign to become exothermic, because this heating curve is an endothermic reaction, whereas the cooling curve is sorry, let me come back again. The heating curve is an endothermic reaction or endothermic process, endothermic physical change, whereas the cooling curve is an exothermic physical change. All right, and that is how you do those. I know it's a little bit long. In exam, I'm not going to actually ask you questions based on trying to do all of them at the same time. I can ask you 2 or 3 phases in exam. However, you're going to see this in your worksheets. So let's now begin to solve more problems. Now, it says most nuclear reactors are cooled by inert gases. It says calculate the number of calories that 3.50 times 10 to the power 3 grams of helium gas will absorb when it is heated from 25 degrees Celsius to 925 degrees Celsius. And the specific heat capacity is given to be this. Remember again, anytime you see a change in temperature and there's no mention of change of state, we're going to use which formula? Remember, Q will be mass times specific heat times a change in temperature. And the temperature went from 25 to 925. So there's a change in temperature. There's no change of heat. If you look at it, there's no change of heat. So to calculate the amount of heat needed, we're going to say 3.50 times 10 to the power of 3 grams. We're going to multiply that by the constant, this constant, 1.25. No, that's a wrong thing I wrote. 1.25 calories per gram per degree Celsius times the change in temperature there we have is T2. It goes from this to this. So this is T2 and this is T1. So it's going to be 925 minus 25. Of course, this in degrees Celsius. And then if we cancel out everything, this will cancel this, this will cancel this. And if you multiply everything together, that will give us 3.94 times 10 to the power of 6 calories. And this becomes our answer. And that is, so anytime it involves a change of temperature, you're going to use this formula. Remember, this formula corresponds to a change in temperature. Whereas if it involves a change of state, you're going to use the formula for the heat of vaporization or the formula for the heat of fission. All right, let's look at the second question. It says, how many calories of heat are required to change the temperature of 1450 grams of water from 25 degrees Celsius to this? Again, this is only change of what? Temperature, no change of state. Again, we're going to use some formula. Mass and the specific capacity of water times change in this. The mass again is 1450 grams. We're going to multiply by it. Now the heat, this is what? Change how many calories are required to change the temperature of water. Remember, when they say water, it's liquid water. The specific capacity is going to be this. So that's what we're going to use. So it's going to be 1.00 calories per gram per degree Celsius times the temperature change from what? Oh, it's even given there. I'll even give it. I don't even have to. I give it there. It's going from it went from 25 to 89. So it's going to be 85.0 minus 25.0, and all this inside degrees Celsius. And again, if we cancel everything, we're going to have our answer to be 92,800 calories of heat is needed for this process that involved a change in temperature. You can always pause your video at this point, try out these problems, and come back and check them for comprehension. Now, the next question says, calculate the heat absorbed when 150 grams of water at 100 degrees Celsius is converted to steam. Look at this question now. Two things are happening here. There's a change in temperature from 100 to 130, and there's what? A change, converted. That's usually the word I use. You can see the change from, always try to read the question because it looks like a word it's a word problem where you must see a word that has to tell you that there's a change of state. So there are two things happening here now. And what can easily help you to figure out this problem is to always know, you can always draw yourself your heating curve. In your heating curve, you start from, this is where you have your solid, it melted, you have your liquid here, you change to gas, and this is only gas. Of course, this is your Q1, Q2, Q3, Q4, and Q5. You can always remember, it helps you to solve these problems. Of course, this is your temperature, and this is your heat, of course. Your calories, and this is degrees Celsius, of course. Don't forget that. This is a typical thing that will help you to solve this problem. So what are the two things happening here? So it says, what is the amount of heat needed absorbed when 150 grams of water? So we are starting from this. You have water of this going to what? 150 grams of water at 100 degrees Celsius. Now listen, it changed. That means you don't have anything here. 150 grams of water at 100 degrees Celsius means you have it at this point. So basically you have a mixture of water and gas at this point. So we're going from 100 to what, about 130 degrees Celsius. So this is what you have. So you're not, so what do you have here now? The question involves Q4 and Q5. So that's basically what you're doing. So your total Q will be, you're calculating the Q4 plus the Q5. That's basically what you're doing here. So what is your Q4? Let's calculate Q4. So Q4, remember, anything here means heat of vaporization is involved. So the formula is going to be mass times heat of vaporization. That's what is involved here. Whereas, so to calculate that, what is it going to give you? What's the mass? The mass is 150 grams. We're going to multiply. What's the heat of vaporization of water? Is this guy is 540. Yeah, that's 540 calories. Let me make sure that is clear enough. It's 540 calories per gram. And when you multiply everything together, remember this is grams, I didn't even put it, this is grams. That will give you, if you multiply it together, that will give you 81,000 calories. Again, you now go to Q5. What is happening in Q5? In Q5, you're changing temperature from 100 to 130. So in Q5, there's a change in temperature, but you still have the same mass, 150 grams times. So remember, Q5 will be, okay, let me just write the formula first. That usually is very important to do just that. I want to write it first. So to write it first, it's going to be mass times, that's what we're looking for, specific capacity of steam. Now you're talking about steam, you're not talking about water. This is steam. That is what is, because this is steam here now. So, and the heat capacity of steam is 0.48 times change in temperature. So if you put everything, it's going to be 150 gram times 0.48 calories per gram per degree Celsius times, what is the change in temperature? The change in temperature is going from 130 to 100. It's going from 100 to 130, and the difference is going to be this. And now, if you cancel out everything, you see, Celsius cancel Celsius, grams cancel gram, and if you multiply everything, it's going to give you 2,160 calories. However, now, the total heat needed for this process will be the addition of the two. So you're going to say 81,000 calories plus 2,160 calories. And if you add everything together, it's going to give you 83,160 calories. And this is the amount of heat needed or absorbed by converting 150 grams of water at 100 degrees Celsius to steam at 130 degrees Celsius. And that is how you can solve this problem. Feel free to pause this video, do these problems, and always come back to them for comprehension. Now, this question is a little bit another long one, but I'm going to be faster with it. By this time, you're supposed to have been picking it up by now. So feel free to pause the video and try this problem. It says, which of the following processes takes the most energy? He gave us a series of processes. I also have another page behind there that is empty, so in case we can also do the problem there. So we're going to try to calculate the energy needed. I know what it is by a snapshot, but as I'm teaching it, I'm going to show you how we do it. So we have to calculate the amount of heat needed for each process. That's what we're going to do. So let's start from the first one. Okay, let me number this. This is 1, 2, 3, 4, 5. And then go to my red. So the first one will be change. Now, melting ice means what? If you're melting 25 grams of ice at this, no change in temperature. So this is basically telling you that you are doing your Q what? Okay, I can draw a little bit of this here. Let me draw it again. This is, so this is Q1, Q2, Q3, Q4, and Q5. So what is going on? What is going on here is that, now remember, this is the solid. It starts melting at this point. So we're melting here. And if you're going to melting, the formula uses the heat of friction formula. So here, the first thing you want to calculate is Q2. So you can easily tell yourself this by knowing the highest one that will give you energy is the Q4. Always the case. You can identify where the Q4 is. And to identify where the Q4 is easy to do that. It is at the boiling. So you can only, you know it's going to be at this. But let's solve the problem ourselves and figure it out. So Q2 is going to be mass times heat of fusion. That's what you have here. So the mass of water we need here is 25 grams for all of them. And you're going to multiply that times 80 calories per gram. You're going to have 2,000 calories. Now for 2, boiling water means change of state here. This change of state. So remember, this is change of state. This is also change of state. Now, so that's what so change of state here is Q4 we're looking at, because there's no change in temperature. It's happening at 100 degrees Celsius. So it's going to be 25 grams. We're multiplying it by the heat of evaporation of water is this, 540 calories per gram. And when you multiply everything out, you're going to get 13,500 calories. That's exactly what you get there, 13,500 calories. Now, we go to the third one. The third one, you are heating from 0 to this. There's a change in temperature. So, and from 0 to this, you're going from what? Look at what is happening there. It's Q what? From 0 to this. That means you're going from 0 to about 20 degrees Celsius. It's involving water. So what are you doing there? You're doing your Q3. So calculate your Q3. Our Q3 is going to just be, again, mass of water. Oh, the mass we have there is 25 grams. It's constant. You're going to multiply that times the specific capacity of Q3 here means only water. And water has a specific capacity of what? 1.0. So you're going to say 1.00 calories per gram per degree Celsius times the change in temperature. You're going from 0 to this. So basically what it's going to be is 20 minus 0 degrees Celsius. And then if you multiply everything together, you're going to get about 500 calories. And let me cancel those ones I've done here. This will cancel this. This will cancel this. And then this we cancel this. This we cancel this to make sure that we are in line. And now the last two will be, now the next one will be the fourth one. You are heating from 25 degrees Celsius, 25 grams of steam from 100 to this. That means we're talking about Q5 here. So in calculating Q5, that's what we're doing. In doing Q5, so Q5, of course, again, is a change of what? Is a change in temperature. Again, from 100 to what? You're going from 100 to 120. So we're going to have the mass, 25 grams, again, times the heat capacity of ice is of steam, 0.48. The same thing with those of ice. This will give you gram per degree Celsius times the change in temperature will be 120 minus 100. And this, of course, in degrees Celsius. And if you cancel this again and multiply everything together, you're going to be getting just this 240 calories. You're going to get 240 calories. That's what you get. And the last but not the least, let's see which stage is that. Is heating 25 grams of ice from, so you're doing Q1. You're going from this is solid to liquid. So that's what you're doing. And again, there's change in temperature. So let's finish it up. It's going to be our Q1. There is what we're going to calculate. It's a change in temperature. Involving change in temperature will be mass. I didn't write the formula for that, so I'm just going to put it directly. So it's going to be 25 grams times. Now, the specific capacity of ice is the same thing with that of water. So it's going to be 0.48 calories gram per degree Celsius times, now 0 minus 20. That's what we have here, remember? And this will be in degrees Celsius. And when you cancel everything again, this is going to give you what? It's going to give you 240 calories. If you look at all of them, this gives you 240. Q1 gives you 240. Q5 gives you 240. Go back. This gives you 500. This gives you 2,000. And it was number 2, which involves Q4, that gave you 13,500. And this will take most energy. And the reason why this thing takes most energy, what's the reason? I would have said, what is the reason for your answer? I would have added that as part of the question. What is the reason for your answer? I can do that in exam. So, yeah, I would have said, okay, give reason. Let's add it. Give reason for that. Let's give reason. So, the reason why that is possible is because it takes more energy, which is potential energy in this case, to break the intermolecular forces. And the intermolecular force here is the hydrogen bond. In water molecule. In liquid water, I'm just in liquid. In liquid water to become steam. So this involves change of state. That is the reason for our answer. The next problem, it says draw the cooling curve for water at a gas phase, removing heat until it becomes solid ice. That's what I told you. When asked to draw, remember what I told you about so the cooling curve is an opposite of the heating curve. I told you that. The difference here is that, what are you doing? The only difference is that it's going to be the direct opposite of that. So let's see how that happens. Remember, in drawing the previous ones, we started from down to up. In this case, I'm going to start from up to down. So remember again, it will always be temperature in degrees Celsius. Now, Now you are removing heat, so you say heat removed. You're removing heat, again it is in calories. You're removing heat. So now we started from here. Now, first of all, okay, let me put this. If you start from here, you are cooling your steam. If you're cooling your steam, at a point your steam is going to be completely what? Condensed to liquid. Then at this point again, what happens? You start condensing it. You condense it until a point you don't have your gas again. Everything becomes liquid at this point. And here now, the liquid will start getting cool. You cool it at a point. It will start freezing at this point. It will freeze, and then you can start cooling the ice again down to this point. So that is exactly what you have here. So here means, let me use a different color. I'm going to use, yeah. So this is steam cooling. You're cooling the steam here. Then here you're now beginning to condense it. You're condensing steam, and at this point you're now beginning to cool liquid water. You're cooling liquid water. At this point you are freezing. You are freezing it. You are freezing liquid water, and at this point you are cooling the ice. And just remember, this process is exothermic because heat is being removed. This is exothermic in nature, and just opposite of what we have in the heating curve. The next problem, and we're getting close to the end of our of this class. It says, how many calories of heat are liberated when 72.3 grams of water at this is converted to what? Ice. Now this is a question involving the heating curve, right? So, and it says draw a cooling curve indicating that process. This is very good to help do it. I usually say to the student, try to always make up a heating curve hypothetically to help you do a problem. So I'm going to make up a quick one. So remember, it is this way. You go longer plateau, you go this one, you go this, and then you go this. This is exactly what you expect to have. Now remember, this will be like the steam. This is the gaseous. So here is going to be 100 degrees Celsius, of course. And then from here, again, it's going to be 0 degrees Celsius. So the 50 degrees Celsius is going to be around here. Remember, this is temperature, degrees Celsius, and this is what? Heat removed. So that is exactly what you're going to do here. So now we're going to try to solve the problem. Now remember, in this case, whatever you're going to use is going to be a negative sign for all these ones, whatever you're going to use. Particularly here, the heat of fusion is going to be negative. If you're doing fission, it's going to be a negative sign. Heat of evaporation is going to be negative. Let's see. So what we want to calculate here now, you can label it whatever you want. So I'm going to label it. Usually the last one I labeled, I started labeling from Q1, Q2. So I can do that. I can call this my Q1. So this is going to be the Q2, right? So this is going to be the Q3. And then, remember Q1, Q2, Q3, Q4, and Q5. So what are we going to calculate? What's the question? It says, how many calories of it are liberated when 72 grams of water? So water at 50 degrees Celsius, we are dealing with Q3, is converted to what? Ice. Ice at what? Oh, so we're going from this to this. So we're talking about Q3 and Q2. That's what we're doing here. So our total Q will give us what? Q2 plus Q3, or Q3 plus Q2, so whichever one. So I'm going to calculate Q3 first because I'm going down. So my Q3, of course, involves liquid water, and there's a change in temperature from 50 degrees from 50 degrees Celsius to 0. So that's what we have there. And what mass? So it's going to be 72.3 grams of water times the specific capacity of liquid water. That's what we have here. Liquid water is going to be 1.00 calories per gram per degree Celsius times, we're going from 50 to 0. So it's going to give us 50 minus 0. Of course, it's in degrees Celsius. And if you remove your unit, whatever you're going to have 3,615 calories. That's what we have in this process. Now let's go to The next one, what about our Q? Now we're moving from Q3 to Q4 to Q2. Q2 means change of state. So in change of state and involves formation of what? Fission. That's exactly what we have there. So we are forming from liquid to solid, or solid to liquid, whichever one. They're going to give you the same thing. So but remember now, the heat of fission here is going to be a negative here. This is going to be a negative sign. So we're going to have what? We're going to have that 72.3 grams times heat of fission. Heat of fission in this case is going to be negative 80. Oh, okay. You see, there's a mistake here. I'm going to fix it. I'm going to fix it. Negative 80 calories per gram. And when you multiply this together, it gives you minus 5,784 calories. Now look at the mistake I made. It's good I figured that out. Remember, I got this wrong. The T1, let's try to fix that. Remember now, the T1, this is going from T2. The T2, this to this means 0 minus 50 degrees Celsius. That is what mistake I made. So I wanted to fix that. Sorry for that. And again, you can now cancel it. So now this is going to give you a negative sign. This is also going to give you a negative. So and now the total heat we're going to get here now is going to be, you add the two of them. Remember, if you add negative 3,615 plus negative plus will give you negative. So it's going to be negative 5,784 calories. And when you add it together, to give you a total of negative 9,399 calories. And this is the amount of heat that is removed when 72.3 grams of water at 50 degrees Celsius is converted to what? Ice at 0 degrees Celsius. And this is how you do this problem. Like I told you, if it is going the other way around, going from ice to liquid, it's endothermic reaction, and this is going to be a positive. So this process, again, like I said, is what? This is exothermic, just to let you know again. The cooling process is exothermic, and that is why we have the negative sign. We go to the next problem. Finally, and that happens to be our last problem in this class. It's been a long ride. Feel free to always pause this video, try out this to yourself, and come back to it. Lastly, it says, how many calories of heat are required to melt? This is an easy question. There's no change in temperature, but you are changing state. So we use the formula for change of state. So if you're going to melt an ice if you're going to make ice at this temperature, that means it's a solid and you are melting it the same temperature. That is at this point. There's no change. Remember, it is our Q2. No change. So in Q2, of course, it's going to be mass times heat of fission. It's endothermic because you are melting. If it is freezing, it becomes exothermic. So now this is going to be 91.3 grams times heat of fission, of course, is this 80 calories per gram. And again, if this cancels this and you multiply, you're going to get 7,304 calories. Thank you once again for listening to this class. If you do have any questions, do not forget the batch channel to contact me. See you later and have a wonderful day ahead of you. Bye.